it comes to electricity, before we can really start to talk about things like electrical force, electrical fields, electrical energy, and electrical power, the stuff that runs our devices, our homes, basically our way of life and allows us to use all the technology that we do, there's a few basic concepts we have to understand about the more elementary topics behind that, which is electric charge. In this video, there's only three things we're going to be taking a look at, so hopefully by the end of this, you are able to analyze these 3 points. The first being the types of electrical charge. What are the types? How do we define them? The second being this concept known as the conservation of charge, which hopefully at this point, conservation of anything is starting to become an underlying theme for the course. And finally, the movement of charge. And we're going to specifically look at the movement of charge within one material before eventually, in some later video, moving on to the movement of charge between different objects. So those are the three topics we're going to take a look at. If any of you have ever touched a doorknob or somebody else and gotten one of those static shocks, that's very simply been a transfer of charge. One of these objects had more charge than the other, and there was a transfer which resulted in this shock or this zap. So if you've ever experienced that, you've actually experienced charge and electrostatics. In order to better understand this concept of charge, we have to go back to a little bit of chemistry and analyze the atom. Hopefully this isn't too much of a refresher, but you have three different things within an atom. You have the protons, the neutrons, and the electrons. The thing that's important to remember right now is that the protons and the neutrons are kind of bound in the nucleus, so they're stuck there. They're not going to move that much. And the electrons, they, for the most part, spin freely, orbiting in the outer shells, and it's significantly easier to pluck these electrons off than it is to pluck off the protons. Protons require much more energy because they're bound by the nucleus, which is exactly why electricity is the flow of electrons, not the flow of protons, because the electrons require significantly less energy to get them to move from atom to atom. So the important thing to take away is that it is the electrons that move and jump from atom to atom. It is not the protons. The second you take a proton away from an atom, it literally becomes a different element, a different atom. So electrons jump from atom to atom, and that's how they flow, so to say, and that's how we get electrical current and how we can get electricity flowing through all of our technological devices. But it becomes very important. Please put some stars by this. We need to realize moving forward that it is the electrons that are moving. The protons do not move. Protons will not move in anything that we look at. It is only the electrons. Bearing that in mind, let's take a look now at the types of electric charge. There are only two types that we discuss, and that would be the positive and negative charge. Positive, if you have less electrons than protons, such as in this case, or a negatively charged object is one that has more electrons than protons. So if you want to know whether an object is positively or negatively charged, simply look at how many protons, how many electrons it has. Whichever it has more of, that will be the dominant charge. Now there's also neutral charge, which is really no charge, and that's when there's the same exact number of electrons and protons. But we don't consider this to be a type of charge because it's really just the absence of charge. So just realize a neutral object, while it has protons and electrons, it really has no overall net charge because for every one proton, there's one electron, and those charges cancel one another out. So neutral is not technically considered a charge, but you'll sometimes hear it discussed during the discussion of a positively charged object, a negatively charged object, and a neutral object. But there are only two types. If you want to know whether it's positive or negative, look at the number of electrons and the number of protons. The next big idea would be this concept of the conservation of charge. And I'll break this down similarly to how I've broken down the conservation of energy, conservation of momentum, and many of the other conservation laws that we've seen in this course so far. So if you were to have a friend and they were to start with $20 and they were to hand you $20, their net gain or loss in this case would be $20. Your friend lost $20 and you therefore gained $20. They couldn't hand you $20 and have you suddenly gain 10. Right? If they lose 20, you'd have to gain all 20. And the same thing applies here. So total between them before was 20. The total after is 20. Now who actually had that money did certainly change hands. But the total amount they both had was always 20. You didn't gain or lose any dollar bills here. The same thing applies for charged objects. So if we take a look at these two objects, we know this is negative because it has 5 protons, but 8 electrons. It has more electrons or negatively charged charges, particles, and therefore has a negative charge. This object has 5 protons, 4 electrons, therefore it is positively charged. It has more protons than electrons. If I look at how many they both have together, I have a total of 10 protons and a total of 12 electrons. So while this object is negative and this object is positive, and they both have varying amounts of electrons, the total protons and electrons should remain constant throughout. So let's assume that in some way, shape, or form, this first object is able to transfer electrons to the second object, and we'll assume that it transfers 4 electrons. Well, that would result in this case. While it originally had 8, it drops to 4, meaning the other object must have gained 4, and it started with 4 and now has 8. They both have the same number of protons because protons do not move in this case. Electrons are the only things that will move when it comes to charge. Well, originally object A or object 1 had more electrons than protons. Now it has less electrons than protons because it's given 4 of them away. You'll notice that the charge on this object went from negative to positive because it gave up enough electrons that it now has more protons. And object 2 is just the opposite. While it originally had more protons and less electrons, by gaining 4 electrons from the other object, it now is negatively charged because it has more electrons. At any point, though, you'll notice there are still 10 protons and 12 electrons between these two objects. At no point does the total change. And it goes back to this same idea of whatever money gained by you is the money lost by your friend. Conservation of anything just means whatever you started with, you must end with. These charges, electrons and protons, cannot be created or destroyed. They can only be transferred between objects. And specifically, the electrons are what we will be considering. The very last of the fundamental things we need to understand is the movement of charge within an object. And more specifically, what we mean by terms that are known as conductors and insulators. And I'll give you a very basic example first. Almost everyone knows by the time you're in first, second, third grade that you should not be taking things like silver or aluminum or metal forks or utensils and sticking them in wall outlets. That is not a good idea. Yet on a daily basis, you take some kind of plug, probably several times a day, and plug it right into that same outlet that you would not stick a knife or a fork into. So the question is, how is one of these situations very bad for us, and one of them that we do numerous times in a day that doesn't really have any negative side effects? And the whole idea comes down to what are known as conductors and insulators. So let's define them first. Conductor is simply any material that allows electrons to freely move. And examples are metals, humans, salt water. These are materials where once electrons are allowed to flow, they will move wherever they want. That's why you have things like lightning rods built out of metal, because if a lightning bolt hits that, it allows those electrons to move through the rod, down the side of your house and into the ground. Humans need to be really careful. You should not necessarily go stand in open fields, because if a lightning bolt hits you, those charges will be able to travel through your body, hitting all your vital organs, and it won't end well. Similarly, salt water, water in general, but salt water more so, you shouldn't go swimming when there's lightning out, because if the lightning hits the water, it will also travel through the water. You're a human, so therefore it'll travel through the water, through you. Conductors, any material in which electrons can move wherever they would like. Insulators, on the other hand, are materials that do not allow electrons to freely move. And examples are glass, rubber, paper, cloth, silk, anything where you can place electrons on them, but they are not free to move. Much like getting stuck in quicksand, once these electrons are placed there, they can't move. They're stuck in that one location. Now, to look back at these two examples, we originally looked at a fork as well as kind of that wire that you plug in every day. Well, if we take a look at the fork, now that we kind of better understand this concept of conductors and insulators, a fork is a metal, which is a conductor. You're a human being. This is your hand, which is also a conductor. So if I were to kind of stick that fork into this outlet, the electrons would then be able to flow through the metal fork because it is a conductor and the electrons can move wherever they'd like. And since you're connected to that fork, they can then travel through you. And they will travel through your body, hitting a lot of vital organs, and it probably won't end well. On the other hand, if we look at the cross-section of the wire is also a conductor. It's usually some copper wire, but it's surrounded by a material that's an insulator, usually some kind of rubber or like latex insulation, some covering. And because of that, as the electrons are freely moving through this copper wire, even though your hand is grabbing the outside of this, they can't travel through this insulator. So they're not able to actually jump into your hand as they were with the metal fork. So if you take a look here, once this is plugged in, the conductor is you yourself. You also have a conductor running down the middle, which is that copper part of the wire. But because there's this insulation, it can't make that jump from the copper wiring on the inside out through the insulator into your hand. And that's the reason why nothing happens when we plug these outlets in, because the electrons are then able to travel through the conductor inside and then to whatever device you'd like, but they're not capable of jumping through this insulator because the electrons can't freely move through there. Now, if there was some kind of hole in this insulation or is very old and crumbling, that's when you need to be more careful. And if you've ever seen one of those old wires where maybe some of the metal is exposed and you've touched it, you may have gotten a shock. Well, that's because this insulation is worn down and you're now giving a pathway from the outlet to your hand. Luckily, there's all sorts of safety features which basically shut the power off in the event that that happens. But the basic idea behind why this is not a problem and this is something you don't want to do, quite simply comes down to the concept of materials that are conductors and materials that are insulators. So hopefully at this point, the three things you're able to understand better are the types of electrical charge, positive and negative. You'll also hear people discuss neutral, but just realize that's not an actual type of charge. Conservation of charge, whatever number of electrons and protons you begin with must be the same you end with. The charge gained by one object is the charge lost by another, and that the movement of charge within an object is solely based on whether that object is a conductor, such as a metal or a human or salt water, or an insulator, such as rubber, glass, cloth, something that does not allow these charges to move.